Hello everybody. Alright, section 6.7 that we're going to start right now. We're going to continue talking about geometric series, but in particular we're going to talk about geometric series that might also be convergent series. That's a new vocabulary term for you. Converge, diverge. Hopefully you're familiar with those words already. Your goal for this lesson, twofold. You will determine whether an infinite geometric series converges, and you will use a formula in order to find the sum of a convergent geometric series. There you go. So those are the two things we're trying to accomplish. I want to take a look at a problem right here. I'm telling you in the goals there that we're trying to determine if an infinite geometric series converges. Well, what I'm really trying to say there is that I want us to determine whether or not you can find the sum of an infinite geometric series. And you might think, how in the world could I add up an infinite amount of numbers and actually get an answer? You know, because for instance, if you add 1 plus 2 plus 3 plus 4 plus 5 plus 6, you're always adding a bigger number, and so you would never actually have an answer for that problem. You would just have to say it's infinity. But it turns out that there are instances where you can keep adding an infinite amount of numbers and you know exactly what all of those numbers are going to add up to. And I have a picture here to illustrate that for you. You see that we're going to use this picture to evaluate the series 1/2 plus 1/4 plus 1/8. Now, notice that that's a geometric series, right? We keep multiplying by 1/2. That will be the common ratio in this series. Well, let me start off with a 1/2. All right, the shaded region right there represents the first term in this series, right? I filled in half of the square. And what I'm going to do then to that is I'm going to add 1/4, or 1/4 of the entire square. And I can create the 1/4 by just dividing this other empty half in half and then shading it as such. And then to add 1/8, well, an eighth is half of a fourth, so let's take this empty fourth right there and divide it in half and shade it. And so forth. Now I have an eighth that's unshaded, and so when I add 1/16, what's the next term? I can divide this in half, shade, then 1/32 would be half of that, 1/64 would be half of that, and so forth. Now I hope you can tell that I keep adding a smaller and a smaller section every time, right? But theoretically, if I were to continue always taking half of the unshaded region and shading it, and then doing half of the next unshaded region and shading it, wouldn't it come pretty close to being this entire square being shaded in? Theoretically, if we did that an infinite number of times, we would actually shade in the entire square, wouldn't we? We'd get to the point where we're adding so little, so little, so little that we've actually come to what's called a sum. Now, that means that this series adds up to 1, which is really pretty cool. We just added up an infinite number of terms, and we found out that they had a definite sum that we were able to find. Now, whenever you have an infinite series and its terms, when you add them together, approach a certain sum, such as number 1 here, that's said to be a convergent series, a converging series, whichever way you want to say it. Converging series have sums. Whereas if I took another series like I mentioned to you before, something like 1 plus 2 plus 4 plus 8 and so forth, that series is never going to have a sum if you continue it on infinitely, because you're always adding something bigger, and so you're just going to end up approaching infinity instead. All right, convergent sums or convergent series have a definite sum. Divergent series don't have a sum. And this one, that one doesn't have a sum. Great. Well, infinite geometric series. Some of them are convergent, such as this one right here. Some of them are divergent, such as that one right there. That was geometric. Common ratio is 2. We need to be able to know whether an infinite geometric series converges or not. And if it does, it turns out it's possible to find the sum of that series. So, how do we know if an infinite geometric series converges? Well, what were the common ratios for those two series that I just showed you? The one that converged, its common ratio was 1/2. The one that diverged its common ratio was 2. And the key thing there was that the one whose common ratio is less than 1 is the one that converged. Now, I'm going to say the absolute value of the common ratio is less than 1 because you could have negative common ratios for a geometric series and still have a convergent sum. If the absolute value of the common ratio is less than 1, then an infinite geometric series is going to converge. And if it converges, that means it has a sum, and the sum is found with this formula right here. Simply u sub 1 divided by 1 minus the common ratio. Now I hope this looks to you a little bit about like the finite geometric series formula that we learned, the version where obviously you do 1 minus r instead of r minus 1. And it actually comes directly from that. I'll try to explain how that is the case. Alright, if we had that complete formula for the sum of the finite geometric series, it would have that 1 minus r to the n right there, okay? And if the common ratio is less than 1, say it's 1/2, and you raise that number to the nth power where n is infinity, well, if you keep taking something like 1/2 and then 1/4, 1/8, you end up getting 0 ultimately for this r to the nth power. And if this r to the nth power becomes 0, then you just have 1 times u sub n, or 1 times u sub 1, or just u sub 1 in your numerator there. So by letting n be infinity, this term becomes 1, that factor becomes 1, and it just gets rid of what I've got in orange right there, and gives us a formula for the sum of an infinite geometric series. Again, only if the common ratio's absolute value is less than 1 will that work. Well, good news is that this formula is a very, very simple one to work with. And so whenever we're finding an infinite sum, it's just not that difficult. Here's where we'll get some questions that you don't need calculators for, unlike the ones with the finite geometric series. Well, let's take a look at a problem example. This example says that in a geometric progression, the third term is 20, the fifth term is 1.25, and it wants us to find the sum to infinity for that series. Well, we need to be able to find out what the first term and the common ratio are in order to use the formula that we learned, the u sub 1 over 1 minus r formula. And so what we're going to need to do then is use the relationship between the fifth and the third term, as we've done so many times at this point, to find out what the common ratio is, and then we could find the first term and find the sum of the series we're looking for. The fifth term would be the third term times the common ratio twice, so that means 1.25 is equal to 20 times r squared. And 1.25 over 20 in a fraction, I know that happens to come out to 1/16. So that's r squared. This 1/16 is what I was referring to. And then the common ratio could either be positive or negative 1/4. And in this case, no real reason for us to assume one over the other. And because of that, I'm going to proceed the rest of the way where I'm saying, well, what if r was positive 1/4 and what if r was negative 1/4? Well, in either case, the absolute value of the common ratio is less than 1, isn't it? So we know that this would be a converging geometric series. Well, then if r is equal to 1/4, how would we find the first term? The first term equals the third term. Well, the third term equals the first term times the common ratio squared. So 20 equals the first term times 1/16, because that's what 1/4 squared is. And then 1/16, if we go ahead and multiply by the reciprocal to get use of 1 by itself, that's going to give us 16 times 20, or 320, is the first term. All right, now I'll continue with that problem and find the sum for that positive common ratio in a moment. Let's look at what the first term would be if we had a negative common ratio. Still, the third term would be the first term times the common ratio squared. Well, the common ratio squared is still going to be 1/16, right? So you'd still have 20 equals u sub 1 times 1/16. And so that's going to give us the first term is 320 either way. Now the sums won't be the same, but the first term is the same no matter whether the common ratio is positive or negative. That's not always the case. It's the case for this one though. All right, now as far as finding the sum to infinity of each of the series for each of these common ratios. All right, if r is equal to positive 1/4, then the sum to infinity is going to equal 320 divided by 1 minus 1/4. Now that's 320 divided by 3/4. And to three significant figures, that's going to get you about 427. If we say the common ratio is negative 1/4, then the sum is going to equal 320 divided by 1 minus 1/4. 1 minus negative 1/4, excuse me. And 1 minus negative 1/4 is 5/4. 320 divided by 5/4 is exactly 256. All right, there you go. Very simple formula to use, isn't it? Let's look at another example. This time we're going to tell you that a geometric series has a first term of 20 and a sum to infinity of 100, and we're going to find the common ratio. Super simple thing to do. All right, remember that the sum to infinity equals, whoops, that's an 8, not an infinity. Sum to infinity equals the first term divided by 1 minus the common ratio, and we know the sum to infinity here is 100. First term is 20. All we're going to have to do in order to find out what r is solve this simple little equation. Well, we're going to get this out of the denominator by multiplying both sides by 1 minus r. I'm going to go ahead and use the distributive property when I do that. It will give me on the left side of the equation 100 minus 100r is equal to 20. So negative 100r equals negative 80. And the common ratio then would be 8/10 or 4/5. Less than 1, which should make sense because we did add this thing up to infinity. That can only happen if the common ratio's absolute value is less than 1. Hey, we only got one more problem to go through. These are really simple, aren't they? This one might be a little bit tougher. Let's see. A geometric series has the sum of its first three terms equal to 58.8, and its sum to infinity is 75. We're going to try to find the sum to 6 terms. Well, here we're mixing a little bit of our finite geometric series with our infinite geometric series. Now let's think about what's going to happen in the end. When we find the sum of the first 6 terms, we're going to need to know what the first term is. And we'll have 1 minus the common ratio to the 6th power divided by 1 minus the common ratio. We still don't know the common ratio and we don't know the first term, so we can't figure that out exactly. All we knew was the n. All right, well, let's look at how we can use these two facts over here to help us with that. All right, now we're going to end up having to use both of these facts in order to find that first term of the common ratio. S sub 3, we can make this equation from that. All right, there's S sub 3, and if this is S sub 3, that means n is equal to 3. The rest of this we didn't know. And from the sum to infinity, we can make this equation. All right, which is a little simpler looking, but it still has a u sub 1 in it, and it still has an r in it. Now we've basically got a system of equations that we're going to use to find u sub 1 and r. And in this case, it's going to work out pretty simply if we will just get u sub 1 by itself in this equation where the sum was to infinity, being the nicer equation. Let's multiply both sides by 1 minus r, and this time I'm not going to distribute, and you'll see why I'm not going to distribute in a moment. It's going to work out really nicely that I don't distribute. All right, so u sub 1 is equal to 75 times 1 minus r. Then I can come over here, and in the other equation that involves s sub 3, I can write 58.8 equals, and then here's where I'm going to substitute. Instead of u sub 1, I'm going to write 75 times 1 minus r. And then I'll still have the 1 minus r cubed over 1 minus r. Now the reason I said this is going to work out very nicely, notice that 1 minus r is a factor of both the numerator and the denominator. And so what we're going to be able to do is simply cancel those out. And it just leaves you then with 75 times 1 minus r cubed on the right side. Let's do a little bit more. Let's go and divide both sides by 75. 58.8 divided by 75 is going to give you 0.784. So that'll be equal to 1 minus r cubed. And then we got a couple of steps to figure out what the common ratio is. Subtract 1, you get negative 0.216 equals negative r cubed. Before we take the cube root of both sides, let's divide them both by negative 1. 0.216 is equal to r cubed. And then the cube root of 0.216 is 0.6. There's our common ratio, is 0.6. Okay? And then to find out what the first term is, we'll come over to this formula. Simply plug in 0.6 for the common ratio. That'll give me 75 times 0.4 equals the first term. And 75 times 0.4 is 30, so that's the first term. And now that we know the first term and we know the common ratio, we can find out what the sum of the first 6 terms is simply by substituting into this formula. Calculator work from here. Go ahead and use your calculator to figure that out. To 3 significant figures, it gives you 71.5. Alright guys, you should see how you use the sum of an infinite, how you find the sum of an infinite geometric series whenever it converges. That's all I've got for you today. Thanks for watching. See ya.